All right, in this lesson, we are going to start looking at piecewise functions. Um, a piecewise function is a function, so it still has to pass the vertical line test. It has to be a function, but it's made up of different pieces. So you can see some examples of piecewise functions here. Um, Basically, it's not one continuous line. It's just there's different parts to it. So there are some piecewise functions for you to look at. The first thing we're going to decide is if different piecewise functions are continuous. Continuous means that you can make the entire graph without ever having to lift up your pencil. Okay, so in this first example here, this line, I could trace this graph and I could make the entire graph and I never have to lift up my pencil. So this one is continuous. Oops. Okay. This one, however, I can get this far and then I have to lift up my pencil to start back up here. So this one is discontinuous. Okay. And then this next one, I could again lift up my pencil to draw the entire thing. So this one would be continuous. I will tell you that every once in a while you're going to see a graph that looks like that, but maybe it has a hole right here. And if I did this and then it had a hole, I'd have to lift up my pencil to draw the rest of the graph, and then it would be discontinuous, just so you know. And then this graph, of course, if I go from here to here, then I have to lift up my pencil to get here. This line is what's called an asymptote. And an asymptote means it's a spot where the graph is undefined or the function doesn't exist. But either way, this would be discontinuous. All right. Then we're going to look at some different properties of graphs here in a minute. This is just sort of optional. I'll do this for those of you that need it. This is asking you to write things in set and interval notation just so that you get used to this. So this is the set of numbers that are greater than 5. If you can do this, then you can skip right over this. But set of numbers that are greater than 5 would look like this. I'd have a hole there because it's greater than, not greater than or equal to, and it would go like this. So in set notation, just to remind you, I would have a parentheses because 5 is not included, and then I would go all the way to infinity. Okay, if the 5 were colored in, I would put a bracket there, just so you know. Okay, then in interval notation, it would go like this. Set of all x such that x is greater than 5. Okay. Here's another one, the set of numbers that are less than or equal to 5. So now it's colored in. I would shade this way. Okay. In set notation, you always do this from left to right. So at this end, I'm still coloring all the way over here, all the way down. So set notation would go from negative infinity, it's colored all the way from negative infinity until I hit exactly 5. Because I hit exactly 5, it's a bracket. Anything at infinity or negative infinity is always a parentheses because you can never exactly reach that destination. Okay? In interval notation, it would look like this. Set of all x such that x is less than or equal to 5. All right, and I think we have one more. Set of numbers that are greater than 5 but less than 7. So greater than 5 but less than 7 would be in here. Okay, and that's what this would look like. I am now colored between 5 and 7. If it would be greater than or equal to at either one of those spots, then they would turn to a bracket instead of a parentheses, just so you remember. And then in interval notation, it would look like this. Set of all x such that x is between, 5 and 7. Go, like that. Sorry. Okay. All right, equal to or greater than 3. Equal to or greater than 3. and less than 4. Set of numbers that are equal to or greater than 3 and less than 4. I actually am going to do less than negative 4, okay? Because I want you to see what that looks like. Okay, less than negative 4. Here's what that would look like in set notation. In set notation, you would be going from negative infinity down here, colored all the way up to negative 4, union, oops, and then I'm colored from exactly 3 until I hit positive infinity. Okay, and then in interval notation, it would look like this. Set of all x such that this little handy dandy little thing here has x values that are less than negative 4. And this handy dandy little thing right here has x values that are greater than or equal to 3. Okay, so you just sort of describe each branch separately. And then the set of numbers that includes all real numbers except for 5. So that means there's a hole right here, and I'm colored everywhere else except for 5. In set notation, I would go like this: negative infinity up to 5, union 5 up to infinity. Okay, so that describes sort of the left half and the right half. In interval notation, this is how the easiest way to write it would be like this: set of all x such that x is a real number, and here's how you write that. X is any number, basically, that's how you say that. X is an element in the real numbers, but x is not 5. Easiest way to write that. Basically, that says it's any number but 5. All right. And we are just going to keep going now. All right, now we're going to analyze some piecewise graphs. So first of all, we're going to look at points of discontinuity. That's where places where the graph has a hole or it doesn't exist. We've talked a little bit about that already. The maximum is the highest point on the graph. Sometimes it's infinity, okay? The minimum is the lowest point on the graph, and sometimes it's negative infinity. Not always, but sometimes. The x-intercept is where the graph crosses the x-axis, and sometimes it never crosses the x-axis, so there isn't one. The y-intercept is where it crosses the y-axis, and again, sometimes it never crosses the y-axis, so there isn't one. Okay. Increasing interval is where the slope is part of the graph where the slope is positive, and so we'll look at that in a minute. And decreasing is the parts of the graph where it has negative slope. And then constant would be parts of the graph where the slope is 0 or where there's a horizontal line is another way to think about that. Okay, the domain is all the possible x values, and the range is all the possible y values. Okay, and then just a little note down here, use parentheses for open circles or infinities or asymptotes, and you use brackets for closed circles. Okay, so we'll kind of go through a couple of graphs here and we'll talk about all of this. All right, so first of all, are there points of discontinuity, and if so, where? And there are points of discontinuity. Discontinuity would mean as you move from left to right, where do you have to lift up your pencil at? And so I could trace this graph from here all the way over here, but then I have to lift up my pencil at x equals 3, and I start again at x equals 4, okay? So my points of discontinuity would be at x is 3 and x is 4. The maximum is the highest highest point the graph reaches anywhere on the entire graph. And you can see that up here it keeps going and going and going and going and going. So it'll go as high as it can, or in this case, it will reach infinity. The minimum value is the lowest point that it reaches. And people are going to be tempted to say that the lowest point down here is at -8. It actually, because it's an open circle, never reaches exactly -8, but it does get really close to -8. Okay, if that circle were colored in, I would say the minimum is -8 because it's an open circle. I just have to say that it gets super duper close to -8, but it never touches it. Okay. The x-intercept. The x-intercept is where it crosses the x-axis, and you are just simply going to have to estimate those because I don't have exact values here. But I would say at maybe, I don't know, -1/3 right there, and maybe 5 1/3-ish. And again, those are an estimate. Okay, so I'm going to say at approximately -1/3 and at approximately 5 1/3. Okay, the y-intercept is where it crosses the y-axis. So that would be this spot right here, which it looks like it happens at 1. All right, then where is the function increasing, decreasing, and constant? So increasing is where it has positive slope. And remember, positive slope means it moves up and to the right. So this section right here has positive slope. Okay, when you describe this, you describe it with your x values. Okay, I describe it with my x values. So down here, this is the point -3, -8. My x value is -3. This is the point 1, 4 up here. My x value is 1. Okay, so it is increasing from -3 up until 1. And I have an open circle at -3. And at 1, I can close it if I want. Honestly, the endpoints on these don't really matter, but we'll practice this. From -3 to 1, it's increasing. Okay, and then here, this is a constant, just so you know. And here, this, although it's not a line, still has positive slope because I go up and to the right. So my coordinate here is at 4, -2. My x value is 4. And then my x value here, as I move off to the right, to the right, to the right, to the right, my x value is going to infinity. So I'm going to do a union, and then I'll have a bracket at 4 to infinity. Again, you describe those with your x values, okay? Decreasing would be graphs that have negative slopes somewhere, so they would look something like that. And I don't have any spots on this graph where it's decreasing, okay? And then the constant part of this graph is right here in this little section where my x value right here is 1 and my x value right here is 3. Okay, again, I go on my x values and not my y values. So my x values go from 1 to 3. And I have at 1, it's colored in, and at 3, it's an open circle. So I'm going to go ahead and put a parentheses. Okay. The domain, and we're going to do this in both set and interval notation. The domain is what your x values can be as you move across the graph. So to do the domain, I'm going to take this line and I'm going to go all the way across and I'm going to see where it's touching the graph. So it starts touching the graph right here when x is about -3. And then it touches all the way till here when x is +3. And then it doesn't touch it anymore. And then it starts again at when my x value is 4. And I go this way. Your domain is always, always, always described with your x values. Okay. So again, it goes from -3 until 4. And those are open circles both places. Sorry, that's not right. It goes right here from the x value of -3 to x value of +3. Union, okay, and then over here it touches again. It starts touching the graph when my x value is exactly 4 until as I move off to the right, it's still technically touching way up top. My x values would be infinity. Okay, if I were to do that in interval notation, I would describe those two sections separately. So this first section here between -3 and 3, it would look like this. X is bigger than -3, but less than 3. Or The green section on the graph would have x values that are greater than or equal to 4. All right, and then the range. The range is your y values. So now I'm going to drag my line this way, and I describe it with my y values. So down here, my y value is -8, and I'm touching the graph, touching the graph, touching the graph, touching, keep touching all the way up to infinity. Okay, so my y values go from -8, oops, not infinity, -8, up to positive infinity. In an interval notation, it would look like this. Set up all y such that basically all my y values are bigger than -8, so y is bigger than -8. All right, we're getting there. Now I want you to use the graph to find f of -2. Basically what that's telling you is that your x value is -2, and I want you to find my y value. So I go to an x value of -2, I go down until I hit the graph, my y value would be -5. Okay, basically what that means is the coordinate -2 and -5 exists on the graph. Okay, it happens. F of 1 means I want you to go to an x value of 1 up until you hit the graph, and my y value is 4. Again, that means the point that 1, 4 exists on the graph. And then f of 3 means I want you to go to an x value of 3 up till you hit the graph, and you can see that at an x value of 3, I have an open circle for my y value, so this actually doesn't exist, and I can't find it. All right, then very last part of this, what is the rate of change or the slope between when x is -3 and x is 1? Okay, so that means I want you to know the slope of this section right in here. Okay, again, the slope is just rise over run, so find two spots where it goes through a corner, and it looks to me like I go up 3, right 1, up 3, right 1, up 3, right 1. So my slope would be 3. All right, different function now. Are there any points of discontinuity on this one? Again, those are places where you would have to lift up your pencil. So I have to lift up my pencil right here when x is -1, and I have to lift up my pencil again when x is 2. So, yep, at x equals -1 and x equals 2. Okay. I next want to know where the function is increasing, and increasing is where it has positive slope. So it has positive slope in here. And again, I describe those with my x values. So my x values there go from -infinity up to -1. Okay. And it is also increasing from here until here. And there, my x values go from 0, I'm going to use a bracket since it exists, all the way up to 2. Okay, decreasing is where it has negative slope, and it has negative slope from here to here. Again, I still describe that with my x values. So my x values in that little section go from -1 up until 0. And then constant would be where it has just a horizontal line, which is this spot, okay? My x values go from really close to 2 up until I hit positive infinity because I keep going to the right, okay? And then we'll talk about the domain. And again, the domain would be what all of your x values can be. So if I were to draw a vertical line anywhere along that graph, a vertical line, and I drag it anywhere along the graph, okay, I'm touching the graph, touching the graph, touching the graph. Even right here, I'm touching the graph because there's a closed circle, and I go and I go and I go, and I touch the graph because there's a closed circle, and I go, and there is absolutely no place where I don't touch the graph, okay? So my domain would go from -infinity to positive infinity. In interval notation, I would say that x is just simply a real number. X can be any number. That's how you write that. Okay? My range means I want to draw a horizontal line and drag it. So now if I drag this, it doesn't look like I'm touching the graph, but if I continue this line down here, I'm actually touching the graph. So I'm touching it, and I'm touching it, touching it, touching it, touching it, still touching the graph, still touching the graph, still touching the graph right here when my y value is 4. Now I'm not touching the graph anymore, okay? So I'm touching the graph from negative infinity until my y value is 4. And this is what we describe there. So basically all my y, as long as my y values are smaller than 4, I'm touching the graph. So I would go from negative infinity up until I hit 4, and 4 is a closed circle, so it'll have a bracket. Or in interval notation, you know what? I have these two switched around. Sorry, I didn't even realize that. These two should be switched, and these two should be switched. Okay, in set notation then, I will have my set of all y's such that y is less than or equal to 4. Okay, and then the next question is, what is the rate of change between when x is 3 and x is 4? So here's where x is 3, and here's where x is 4, and my rate of change in here, since it's a constant, my rate of change would be 0. All right, and that should do it for this lesson.